Turning sunshine into usable electricity feels like a modern-day marvel of advanced technology. But what if I told you that solar photovoltaics, turning photons into electricity, is not modern at all and was in fact discovered over 170 years ago? Solar photovoltaics, or solar PV, is often used as the symbol of renewable energy, one of the foundation technologies. So, what is it and how does it work? The photovoltaic effect, converting light directly into electricity, was first discovered in 1839 by French physicist Alexandre Becquerel. If we use some imagination, picture a photon as a tiny parcel of light. When photons strike or are absorbed by the right sort of materials, they effectively knock electrons out of their natural spot in an atom. This creates a hole with a positive charge and an electron with a negative charge. Now this electron-hole pair, they want to recombine because they are more stable together than apart. But by using the right combination of materials, we can entice this electron to travel around an electrical circuit before it recombines with the hole. And in so doing, we create electricity, which is simply the movement of electrons. Modern solar PV cells, which are the building blocks of a solar PV module or panel, are made from layers of semiconductors, such as silicon. There are two types of semiconductors that combine to form solar cells. The P-type, P for positive, which carry the holes or positive charges, and the N-type, N for negative, which carry electrons or negative charges. The material science that goes into making P-type and N-type semiconductors is a huge area of complex research. But in essence, they are created by doping the semiconductor with other elements or compounds. These elements either take away weakly bound electrons for P-type semiconductors, making the material more effective at carrying holes or positive charge, or they give away weakly bound electrons for N-type semiconductors, making them more effective at carrying negative charge. Layering these materials together gives us a way of separating the electron-hole pair after it's formed and harnessing those electrons to do work for us. Many solar PV cells are combined to create a solar PV module or panel. These are in turn put together to create larger solar PV arrays. Several standard electrical components are also required to produce a complete solar PV system. Solar PV generally operates at a capacity factor of around 20%, whilst the efficiency of commercially available cells, for example for rooftop and utility applications such as large solar fields, it currently ranges from about 8 to about 20%. There are several common varieties of solar PV panels. The most common is crystalline silicon. This is what we generally see on rooftops and in utility scale applications. They are a mature technology and form about 80% of the market. Efficiency is typically between, say, 15 and 20%, and modules typically generate about 150 to 250 watts of power. The next most common are the thin film PV modules. These basically make up the remainder of the market, and whilst the thin film products are available, are a mix of mature and developing technologies, their efficiencies are generally lower than their crystalline silicon counterparts, typically ranging between 8 and 12%. Because of this, the modules generate less power, maybe 150 watts. Importantly, thin film solar PV panels require a range of less available elements than the crystalline silicon, which has led to some questions about their long-term viability. There are also more exotic varieties available, with researchers using flexible plastic materials and organic dyes to develop solar PV cells for a greater range of applications, such as attaching to building materials or even to your clothing. This flexibility comes at the cost of reduced efficiency, which is typically less than 5%. One of the most promising new technologies are perovskite materials, which have seen unparalleled increases in efficiency in just a few short years. Their performance now rivals state-of-the-art silicon cells, but they are not very stable when they're exposed to the elements. The last alternative I want to talk about here is where we concentrate the power of the sun by using mirrors or reflective surfaces and aiming it at very high efficiency but high cost solar cells. This version is known as concentrated solar PV, and it can achieve efficiencies of up to 40%. They are a mature technology, used mostly in utility applications due to their size, maintenance needs, and their requirement to constantly track the trajectory of the sun in order to concentrate solar radiation onto the small solar cell. We need to remember that concentrated solar PV is not to be confused with concentrated solar thermal, even though they have lots of similarities. Now that we have an understanding of the range of solar PV technologies available, let's have a look at the main factors, both inherent and environmental, that determine the performance of solar PV cells. These could include capacity factor, conversion efficiency, sunlight intensity, shadow, and temperature. Let's start with capacity factor. This refers to the proportion of actual power generated versus the maximum theoretical power that could be generated. For solar PV, this is generally around 20%. Obviously, there are 24 hours in the day, and the sun is only up and shining long enough for solar PV to generate significant amounts of electricity for about 1/5 to 1/4 of this time. To get a perspective on the range of conversion efficiencies in solar PV technologies, here's a chart comparing the efficiency of common PV products. On the horizontal axis is conversion efficiency. That line at about 33.7% is the Shockley-Kessel limit. This is the theoretical limit of efficiency of a single PN junction cell. But let's take a minute to examine what we mean by efficiency for solar PV. Remember that electrical efficiency means the ratio of electricity out to the amount of incoming energy, which in this case is solar energy. Well, let's consider that we have an area of land that receives about 200 watts per square metre on average. If we cover that whole square metre with solar panels that have an efficiency of about 10%, then we will generate 20 watts of electricity. The intensity of the available sunlight is another important factor and effectively dictates the capacity factor for solar PV. Essentially, the power coming out of a solar PV cell is in direct proportion to the amount of sunlight that hits it. The more solar energy that hits the solar cell, the more electrical current that will be generated. The efficiency of the solar PV cell is only minimally affected by sunlight intensity, meaning that the ratio of incoming photons that get converted to electrons doesn't change. Rather, a reduction in sunlight intensity just means that there are fewer total photons coming in, and so there are proportionally fewer electrons being generated. Shadow, the most common of which are clouds, have a significant effect on electricity production. Shadowed panels produce little to no electricity. If this occurs on solar PV arrays that are arranged in series, and by that we mean that the panels are part of a long chain, then the shadowed panels will continue to carry current generated by the other panels, but with slightly increased resistance. This means that current will drop, and to maintain the load, the voltage of the non-shaded panels will correspondingly increase. But with increasing shade cover, the overall voltage will drop below the operating voltage, and eventually the flow of electrons will fall to zero, and you will get no power from your panels. To avoid this, we can use what is called a bypass diode, which allows the current to bypass the shadowed panels exhibiting higher resistance and minimize the overall impact of shadows. Temperature also has a significant effect on solar PV performance. Although counterintuitive, as the temperature increases, solar PV cells actually become less efficient. And as the temperature decreases, solar PV cells become more efficient. This leads to the situation where there is a trade-off between sunlight intensity and temperature. Solar PV in a region far from the equator, such as Europe, will receive less sunlight, but it will convert that sunlight with greater efficiency, whilst the opposite will occur for a region close to the equator. This is really only a problem in hot desert areas, which unfortunately also corresponds with some of our best solar resources around. So, there are two major solar PV technologies today, with crystalline silicon forming the base of our market. There is a clear case for research into developing other varieties in order to achieve greater conversion efficiencies, lower the cost, and improve the panel stability. We've come a long way since Alexander Becquerel first observed the photovoltaic effect. It's clear that the more we discover about this phenomenon, the more we can apply it to harness the amazing resource that is the sun.